Hi everyone, and welcome to part 8 of this video tutorials. In this video we are going to look at how to read in BaseMaterials RGBA colors and send these values to our shaders for rendering. We are also going to switch to a new shader style to better see the mesh topology. And finally, we will apply proper transformation to our meshes so they will position correctly inside the scene. Alright, so the first thing that we need to do is to write a new utility function to convert hexa values to decimal numbers for each of RGBA channels. So as you've already seen, the values that we have inside the display color is stored as hexadecimal, and we need to convert these guys to decimal numbers. Now, if you go to this website called webpage.fx, you can type in the hexadecimal number and get the RGB value for them. So let me go ahead and copy these numbers here, and we don't need to add the last one, which is the alpha channel. And let me just type it here. You don't also need to include this sign number, so you can just type it like this. And as you can see, you get the RGB or decimal numbers for these values. All right. You can also have a look at this website that basically talks about how the hexadecimal conversion to decimal number works. And as you know, a hexadecimal number has a base 16 that goes from 0 to F. And if I were to type EC here, you can see that we are getting 236, and this is how it calculated this number and gave us this. Alright, so we basically need to write a function to do this conversion. So let's go back to our code and add this function in our import 3mf. Okay. Alright, so here is our converter function called hex to RGB that takes a string, okay, by reference, and converts it to I16 vec4 type and returns it, okay? So basically, the return type is a 16-bit signed integer for each of the vectors component. Since we have RGBA, 16-bit is good enough for us. And once inside this function, you can see that we are creating a new object called color. Then we drop the hash if the value has 1. We don't really care about this number sign. And once we have that, we need to operate on this string and extract EC, 1B, 23, and FF. Okay, so to do this, we use input strings string, and we subtract these values. So we start from 0 characters, so which is E, and we need 2 of this guy, so the position would be 2, and we then use std hex to convert our hexadecimal to decimal number and store it in the R channel. Okay, we are gonna do the same thing for the remaining channels that we have. So the next time we want the value, so let me just copy this thing so you can see this better. So we drop this number, we found out this guy. Next we are going to position our character here, and we need 2 of this character, so 1B, and once we have that, we just convert it to decimal number, and we store it in the G channel. Next, we move on to the 4th one. So we've already done this, so the starting position starts from here. Okay, and we do the same thing for the rest of this guy, and once this is done, we just simply return the color. Okay, a very simple function, and that's all it goes with this function. All right, so now that we've done this conversion, we need to find out the colors that are assigned to each triangles based on the PID and P-index. And as you know, each of these triangles has a PID and P-index assigned to them. And since in this case we have only one color, we are not writing these values at the triangles level and rather in the object level. Alright, so we now need to go ahead and find out what these numbers are. Okay, to find out the PID and P-index, we need to go back to the place where we were iterating through each faces, which is basically happening inside a save mesh data per item. So as you can remember, here is where we are iterating through the vertices, and this is the place where we are actually iterating through each of the faces. So we need to add our code inside here, this for loop, to access this PID and P-index. Alright, so let me go ahead and add the code for this. Alright, so here is the new code that I just added, and I also included a new header file called NMR mesh information basematerials.h. If we go inside this header file, you can see that this header file defines the BaseMaterials information class. So here is our new class called C information BaseMaterials that derives from the C information. Okay, and this is the function that this is the class that we are using here. All right, so what I did was we know that the P information that we have is a CMesh information type, so this is the type of the pointer for this, and I can simply cast this to CMesh information base materials. We already know that this is a base material, this pointer is a base material type. Okay, so now that we cast to this new pointer, we can go ahead and grab the mesh information base material. So if we take a look at NMR mesh information types, you can see that we have a new structure here, and this structure is the one that basically holds to the PID and the P-index that you see inside here. Alright, now to do this, what we need to do is to reinterpret cast to this new pointer, and we simply call the get face data, which is basically part of C information base class. So if you look at the C information, which is a base class for handling all the mesh related linear information such as face colors and textures, we have this routine called get face data. And the type of the pointer that we have here is NF byte, which is simply an unsigned char. Alright, so that's how we can access to this pointer by doing reinterpret cast. Okay, so once we have this new pointer p face data, we are now ready to extract the PID and P indices. Okay, so here I have a model resource ID PID, and I just call the MN material group ID of this P-face data, and I do the same thing for the P-index by calling MN material index, and once I have this, I simply print out these values. Alright, so let's go ahead inside Visual Studio and let's compile our code just to see if everything is okay. And let's go ahead inside main app and change our 3MF files to cube base material. Okay, and let's run this code and see if we can see our PID and P indexes. Great. So as you can see, we are printing out the PID and P index for each of our triangles. All right. So now that we have extracted PID and P index, we can now go ahead and use them to look up the base materials and find out what the colors are for each face. So we can basically, let me close this. Let's go back into our code. So we can use this PID and P index to look up the base materials element and find out what colors assigned to each face. All right. in this example, we only have one base materials element, but there are other examples that you might have more than just one base materials. So you can have another base materials with ID 2, and this one can have more than one color. Okay, so you're gonna end up having more colors inside here. So again, we need to cover this case that might happen if we have more than one base materials. And you'll see in a moment how we can actually handle all these cases. Alright, so let me undo all this change. Okay, let me go ahead and add the code for what we need to do to grab these values. Okay, so the first thing I added here is these two new header files called NMR model base material and NMR model base materials. Okay, and we now also have two new key value paired containers called p index to color value and PID to base materials. So let me explain what the first map does. The first map that we have is an unordered map. And in this case, we don't actually need to sort the data that we have. All right. So with the way that we are parsing our data, ordering does not matter. So we can simply use the unordered map, and the key for this map is model resource index, which is basically the p index, and the value for that is this display color value, which is a string. Okay, so let's say if I were to have more base colors here, so I would say this is blue and this is some other color like green, just making these things up. Okay, what we need is we have the index, so this is index 0, this is index 1, and this is index 2. Okay, so the key here is this indices, and the value that we get is this display colors. Okay, so that's all this map does. Let me undo these changes. All right, the second map that we have is again an unordered map, and the key this time is the PID, and the value is this map that we just saw. Okay, so as we saw earlier, we could have cases where we would have more base materials. Okay, and let's say this base material can be ID2, and this face, for instance, can refer to these base materials and a color that is inside here. All right, so we need to cover this case as well. So that's why we have this second map as well. Now, once we have our maps, we have this new function that basically returns the PID to base materials. And you see in a moment how I'm actually calling this function. So this function is basically taking a P model, okay? And once we are inside this function, we create the maps. So we create the P index to color value and PID to base materials maps. And we basically need to loop through our model. So our model actually gives us the base material count, and in this case we only have one base materials element, so this number would be 1. And then we have a second loop that basically returns the colors that are inside here. Okay, and in this case again we only have one base color, which is a red color. Okay, now inside this loop, we basically need to access the display color value. Okay, we know what the index is. The index for this map is J. Okay, and the value that we need is P material. So from P material we can get the base material, and basically we can call get display color string. So if we look at the header files that we just added, okay, inside NMR model base material.h, you can actually see that we have this convenient function called get display color string that returns this hexadecimal value. All right. So again, we insert all these things into this map. And once we are outside of this for loop, we also need to insert the PID. Okay, so to get the PID, it's a little bit long. You need to actually get the base material resource I, okay, and then get the resource ID, get unique ID, which basically gives us this PID, and the value that we want is the map. So the map is index to color value. All right, and once we are done with inserting our values, we just simply return ID to base materials. All right, so that's all we need with this. That's all we have with this function. And let's go ahead and see how we are calling this function. Okay, now inside our read data, we basically call this base material data. We pass our p model to this function, and once we get this return type, which is a PID to base materials, we need to pass it to our save mesh data per item. Okay, so we pass this by reference to our function. So now our save mesh data per item is taking this map by pointer, by reference, and inside here you will see that I changed the order that we are parsing the vertices and triangles, and you will see in a moment why I had to do this. So inside here, line 114, we create a new base material color, and this is GLM vec 4. And when we are looping through or iterating through our faces, you saw that we grab our PID and P indices. So now I can look up our maps, and I can find out these values that are associated with each triangle. So the first thing is, for the base material map, I'll pass in the PID, and I try to find it here, and we get this new iterator, and with this iterator we can see if we actually have this element inside our map. So if we have it, and if we found it, we basically get the second, which is our map value, so this index to color value, and we find out the P index inside here. So we search for the P index inside this map, okay? And the second 5 also gives us this new iterator. With this iterator, we can actually go through this map and see if it exists. We can grab the value, which is this display color hex, and store it in our RGB values, okay? So once we have our RGBA colors, I can basically pass it to our base material color, and this is a floating value, so I have to divide all the channels by 255. All right, hopefully this makes sense. And once we have this base material, this is pretty much the actual color that we have for each triangle. Okay, now previously I was iterating through the vertices before our triangles. So we had the code here, and with the way that we are parsing our data, this is almost impossible to actually pass in our base materials color easily to our vertex color. So in this case, I just changed the order. So we do our triangles first, and then we find out the base materials, because that's the only way we can actually grab our base material color at the moment. And once we have that, we then loop through our vertices and we fill out this color with this base material. Okay, hopefully this makes sense. And again, this is one way of parsing data, and as you know, we have the limitation at the moment that we assume that all the vertices have the same color. Okay, so we don't have any color gradients or anything, it's just a solid color for all the vertices. Okay, now with this change, we should be able now to see our colors, and let's go ahead inside Visual Studio. Let's compile and just make sure that everything is good. All right, and let's run the app. So let me just make sure what model we are loading. So inside our main app, if I can find it. So we are now loading our cube base materials. So if I run this, we should see our red base material. That's great. Let's go ahead and do more tests. Let's pass in our keychain, and let me show you how our keychain looks like. Okay, so this is the keychain that we have. So we have 5 different colors. We have white, green, orange, yellow, and blue. So let's go ahead and test our code to see if we can actually load these base materials correctly. Great. So it looks like that our code is actually working. We are able to see the base materials correctly. Great. Let me close this. Let me also load this rocket model and just see if it comes up right too. It should be fine. Let's just load this. All right. So yes. The color comes fine, and let me also change the the background color. So let's change it back to 1. Great. So the next thing that we need to do is to change our shader and make it a little bit better to see the mesh topology. At the moment, the shader that we are using is just a simple per vertex color, and there is no lighting, and there is no flat shading going on, so we cannot see the topology of the mesh very well. So let's go ahead and add this new shader, and you can find out about this shader a little bit more by looking at this website. It's a very nice website, and it talks about the flat shading or wireframing, and basically there are 2 ways of creating these shaders. One is by using the derivatives, and the other one is by using geometry shader. In this video tutorial, I'm just going to use the derivatives and not going to use the geometry, but you can actually read these articles and find out how to do that. It's a very nice article that explains exactly how we can actually achieve the flat shading by either using derivatives or geometry shaders. And I'm also going to include this link inside the description of this video. Alright, so let me go ahead and add our new shaders so we can actually see our rocket model a little bit better. Alright, so here is our new shader called Faceted Shader, and inside the vertex shader we have 2 varying variables called word, pose, and color, which we then pass into our fragment shader. Inside our vertex shader, we need to find out the color per vertex as well as the position per vertex. To calculate the word position, we can simply use the model view matrix and find out the word position for each of the vertices, which we then use inside the fragment shader when we use these 2 derivative functions. So the main thing that needs to happen here is to basically find out the normals by using the screen space derivatives. Okay, so we need to basically construct these normals, and in order to get our lighting working, we actually need this normal value. Now, if we look at our core mesh data, you can see that we don't have a normal values for our vertices. Okay, so we don't really need the normal inside this structure. We are actually calculating the normal inside our fragment shader. Okay, and if we look at the light formula, you can see that now we have this normal vector, okay, which we constructed using the derivative functions, and we now gonna go and construct a new vector for the light, okay, and this is where the light is positioned. And basically we now can calculate the angle between our light and normal. Okay, so if we look at our shader inside here, you can see that now we have our normal vector constructed, and then we have two lights. Okay, you can have more lights, but I just added two lights because that, I think, is good enough for what we want. And basically we have one light which is right above us on the y-axis, so it's 1 5 1. I normalize this vector, and then I have the light color, and the color is just pure white color. And basically what I would do is I calculate the dot product of the normal as with the light dir0, which is this guy. And as you know, the value that we get for the dot product is a scalar value, which is between -1 and 1, and I can't really use that, so I need to basically change the range from -1 to 1 to 0 and 1, which I can easily do by using the clamp function. Now, once I have this value, I can just multiply it by this light color that I have, and I simply add it to our diffuse. Okay, inside here I do pretty much the same thing for the second light, and once I have that, I can simply add in the per vertex color to this diffuse. So I can just multiply that by our diffuse, and then I pass the diffuse to our fragment. Okay, and for alpha I just need to pass in the color dot A. Okay, we don't really care about this alpha, it's always 255. Now let's go ahead and inside our main app, let's see what we have. So inside our main app, let me close this. So inside the header files, you can see that we now have a new shader called Faceted Shader, and we basically create a new this shader by passing the Faceted Shader vertex and fragment shader. And once we do that, we just pass in this shader object to our draw function. All right. So instead of using vertex shader, now we are switching to Faceted Shader. Now let's go ahead and run our program and see how things are gonna look like. Very nice. So as you can see now, we have a flat shading going on right now, and you can actually see the topology of this mesh a little bit better. The light is a little bit blown over here, it's too much, but we can adjust this in our shader if we want to. And let me go ahead and load in a few more models and see how things are look like. So let me even move this up a little bit to see our mesh a little bit better. Okay, let me go ahead and load in the keychain, for instance. Perfect. So as you can see, we can see all the faces and everything here. It looks nice. Let me go ahead inside 3D Builder and let's create a few more models. So let me go ahead inside the library and see what else they have. Let's load this train model. Okay, Let me go ahead and change these colors a little bit. Maybe we have something like, I don't know, blue here for this guy. I'm just trying to use unique colors as much as I can. So let me create like green for this guy. What is like this guy? And maybe for this guy, let me load something like this. Okay. So we have different colors for this train model. Let's save it and see how it looks. What do I call this? Train. Yeah, train engine. So let's call this train. Okay. All right. So again, we don't see this train model, and the reason for this is basically we are right now ignoring the transformations that we have at the item level. So if you look at basically our 3D model, you can see that right now we are simply ignoring this transformation that is happening over here, and this is very important for us because we want to respect this transformation and we need to have this transformation. Okay, so that's the reason why every time we load our stuff, like our models, they don't look quite correctly. So if I bring, for instance, our cube base material, if I run this code, you can see that our cube is not at the origin. If you look at the 3D builder, so if I go into 3D builder and if I load our cube, you can see that our cube is sitting at the origin. Okay, regardless of the unit that we have inside here, the cube is here. Okay, if I bring any of our models that we have, they are all at the origin. So if I bring the keychain model, you can see that it's inside here. Okay, it's in, oops, I deleted that. You can see that this keychain is sitting in at the origin. Okay, now here is what we are gonna do next. We are gonna actually apply the transformation to our meshes so they actually end up correctly inside the scene. Okay. Another thing to also notice is that with 3D Builder, the z-axis seems to be pointing up, and in our program, y is actually pointing up. Okay, so that's why the orientation is a little bit different, but nonetheless, we should be okay by changing our code so we can respect that. Again, this is not very necessarily to do right now, but what is important is to actually get the transformation correct. Alright, so inside our import 3MF CPP, we have a new function called getItemTransform which simply returns a 4x4 matrix, and this is a GLM matrix, and we are passing the P model and P model P item to this function. Inside here, the first thing that we need is to get the transformations for item, and we do that by calling item get transform function, and this function basically returns the lib3mf matrix, which is NMATRIX3. Okay, if you look at this NMR geometry.h, you can see that even though it says NMATRIX3, this is defined as a 4x4, and as you know, the affine matrix represents a 3x3 matrix and an associated translate vector. So in other way, you can think of this as a 4x4 matrix where the final column is set to 0, 0, 1. Okay? Now, if you look at the documentation that comes with 3MF, or it's inside the 3MF specification, you can see that in the section 3D matrices, it is mentioned that this matrix is actually a row major. Okay, now since we are using a GLM library, all the matrices are actually column major, so we have to keep that in mind when we are actually going from the netfab matrix to the GLM matrix. Alright, so we'll see in the moment how we do that. After that, I'm creating a new 4x4 matrix for scaling, and I no longer multiply this unit scale scalar value by our vertices. So I used to actually multiply it here, and we no longer need to do that. And I call the GLM scale, which you can find inside a matrix transform, so you actually have to include this header file. You basically pass in your matrix and the scalar value that you want. Okay, I call this matrix M for now. The next thing that we need to do is to create our column major matrix for our transformation, and basically we can do this by setting up our column majors. And the way that you do that, if you pass in these values like this to your GLM 4x4 matrix, keep in mind that this is actually setting up the first column. So this is setting up the first column, and this is a second column. This is third, and the last one is fourth column. Alright. So this is how we actually create our new matrix. Now, once we have this, I'm gonna multiply our scale matrix, which is a 4x4, by this new affine transform matrix. Okay, and keep in mind that the order that we are multiplying is important. So I multiply M by T. Okay, and once it's done, I simply return T. Okay, now let's go ahead and see how we are actually calling this function. So down here inside read data, every time we iterate through this build elements, we actually call this a get item transform, and we pass in our model, model and item, and I get the reference to the return type that this function has, and I simply pass it to our save mesh data per item. So now if we look at the save mesh data per item, you can see that I'm passing this transform, and all the way when we are creating our PMesh model, there is this new routine called set affine transform, which I actually pass in by pass this transform to it. Now let's go ahead and see how we have this set assign transform created. Now, if we go inside the mesh draw header, you can see that our interface has two new functions. One is called set affine transform and the other one is called get affine transform. And we also have this new protected member variable called m_affine transform matrix, which is set to an identity matrix. And basically, anybody who drives from this mesh draw, they have to implement these two functions. So if you look at mesh line, you see that we are overwriting these two functions, and inside our mesh line, you can see that we are actually sending this m_affine transform matrix to our shader. Okay, similar thing is also happening with the mesh model. So we have the same we have these two function, as well as if you go to CPP, you can see that I'm actually passing this m_affine transform matrix to our shader. Okay, so that's how we pass our transformation all the way to our shader. All right, hopefully this makes sense. And let's go ahead inside our main app, and yes, we have our train engine now loaded. So let's go ahead and run this code. Perfect. Now, as you can see, we can see our train model. If I go ahead and comment out the code that we have in our 3MF, import 3MF, you can see why previously we were not seeing this model. So if I comment out this line and just run this, okay, we basically do see our model, but the scaling is not being applied, so we don't see that. So let me do this. Let me go ahead where we are actually doing the set transform. So if I don't do the set transform altogether, then we should not see our model. Okay, and there you have it. So let me go ahead and let me undo this change. Okay, and let's go inside 3D Builder and let's create another model. So inside here, I'm gonna bring these alphabets. So let me bring these guys. All right, and let's save this. Okay. And let's load these guys. Perfect. So as you can see, we were actually able to load our model and apply the transformation correctly, and that's the final result that we get. All right, so this should conclude part 8 of this video tutorials, and I hope you found this tutorial useful, and hope to see you in the next video. Thanks.